In the name of Almighty God, I'm Mahsa Sankosha, and today I want to have an overview of stress strain analysis for elasticity equations. The present chapter and simulation contains the analysis of strain, and stress strain relationship to particular sections. The theory of elasticity contains equilibrium equations relating to the stress, kinematic equations relating to the strain and displacement, and constitutive equations relating to the stresses and strains. Concept of normal and shear stresses, principal stress, plane stress, Morse-scale stress invariance, and stress equilibrium relations are discussed in analysis of stress section, while strain displacement relationship for normal and shear stress compatibility of strains are discussed in analysis of strain section through geometrical representations. Linear elasticity, generalized Hooke's law, and stress-strain relations for triclinic, monoclinic, orthotropic, transversely isotropic, fiber-reinforced, and isotropic materials with some important relation for elasticity are discussed here. If the external forces producing deformation don't exceed a certain limit, the deformation disappears with the removal of the forces. Thus, the elastic behavior implies the absence of any permanent deformation. Every engineering material composite possesses a certain extent of elasticity. The common materials of construction would remain elastic only for small strains before exhibiting either plastic straining or brittle failure. However, natural polymeric composites show elasticity over a wider range, and the widespread use of natural rubber and similar composites motivated the development of the field elasticity. The mathematical theory of elasticity is possessed with an endeavor to decrease the computation for condition of strain or relative displacement inside a solid body which is liable to the activity of an equilibrating arrangement of forces, or is in a condition of little inward relating and relative motion, and which tries to obtain results which might have been basically essential applications to design, building, and all other helpful expressions in which the material of the development is solid. The elastic properties of continuous materials are determined by the underlying molecular structure, but the relation between material properties and the molecular structure and arrangement in materials is complicated. There are wide classes of materials that might be portrayed by a couple of material constants which can be determined by a microscopic experiments. The quantity of such constant relies upon the nature of the crystalline structure of the material. In this section, we give a short but then entire composition of the basic highlights of applied elasticity having pertinence to our topics. This praise-worthy tutorial, likely the most successful and best surely understood theory of elasticity, have been given numerous excellent and comprehensive compositions. Researchers whose use of direct notation and we find appropriate to avoid encumbering conceptual developments with component-wise expressions. Other researchers gave an overview of engineering mechanics in their book, and Podi discussed the strain and examples of concentrated contact interactions in simple bodies in the primer of elasticity. Interestingly, no matter how early in the history of elasticity, the consequences of concentrated load were studied. Some of those went overlooked until very recently. The problem of the determination of stress and strain fields in the elastic solids are discussed by many researchers. Biffle and his colleagues discussed the stresses in elastic plates reinforced by fiber lying in concentric circles, and Biot gave the theory for propagation of elastic waves in an initially stressed and fluid saturated transversely isotropic media. Bouchard studied the propagation of surface waves in viscoelastic layered media. The fundamental study of seismic surface waves due to the theory of the linear viscoelasticity and stress-strain relationship is elaborated by some notable researchers. The stress intensity factor is computed due to the diffraction of plane dilation waves by a finite crack by Chang. Magnetoelastic shear waves in an infinite self-reinforced plate by other researchers, and the propagation of edge wave under initial stress is discussed by Das. and existence and uniqueness of edge waves in generally anisotropic laminated elastic plates by Fu, and the basic and historical literature about the statistical relationship for propagation of elastic waves in kinds of medium is given by some eminent researchers. Researchers have discussed the propagation of essential edge waves in semi-infinite isotropic plates, shells, and incompressible plates under the influence of initial stresses. The theory of boundary layers in highly anisotropic and reinforced elasticity is studied by Hall and other researchers. This chapter of simulation addresses the analysis of stress, analysis of strain, and stress-strain relationship through particular sections, concept of normal and shear stress, principal stress, plane stress, Morse cycle, stress invariance, and stress equilibrium relationships are discussed in analysis of stress section, while strain displacement relationship for normal and shear strains, compatibility of strains are discussed in analysis of strain section through geometrical representation too. Linear elasticity, generalized Hooke's law, and stress-strain relation for triclinic, monoclinic, orthotropic, transversely isotropic, and isotropic materials are discussed, and some important relations for elasticity are deliberated. Analysis of stress. A body consists of huge number of grains or molecules. The internal forces act between a body, representing the interaction between the grains or molecules of the body. In general, if a body is in a statistical equilibrium, the internal forces are equilibrated on the basis of Newton's third law. The internal forces are always present even to external forces are not active. To examine these internal forces at the point O in this figure, inside the body consider a plane MM passing to the point O. If the plane is divided into a number of small areas, as in the figure, and the forces acting on each of these are measured, it will be observed that these forces vary from one small area to the next. On the small area delta R at point O, a force delta phi F will be acting as shown in this figure. From this concept of stress as internal force per unit area can be understood, assuming that the material is continuous. The term stress at any point after a small area delta R can be defined by the limiting equations as below. Stress sigma is equal to delta F divided by delta R, where delta F is the internal force on the area of delta R surrounding the given point. Forces which act on the element of material may be of two types. The first is body forces, and the next one is surface forces. Body forces always act on every molecules of a body and are proportional to the volume, whereas surface forces acts over the surface of the body and is measured in terms of force per unit area. The force acting on a surface may resolve into normal stress and shear stress. Normal stress may be tensile or compressive in nature. Positive side of normal stress is for tensile stress, whilst negative side is for compressive. Stress components. Three mutually perpendicular coordinates, axes x, y, and z, are taken. We consider the stresses act on the surface of the cubic element of the substance. When a force is applied as mean, that the state of stress is perfectly homogeneous throughout the element and that the body is in equilibrium as shown here in this simulation. There are 9 quantities which are acting on the faces of the cubic and are known as the stress components. The principal stress and strain invariants. Let us consider three mutually perpendicular planes in which shear stress is zero, and on these planes the normal stresses have maximum or minimum values. These normal stresses are referred to as principal stresses, and the plane in the which these normal stresses act is called principal plane. Invariant mean those amounts that are unchangeable and don't differ under various conditions. With regards to stress components, invariants are such quantities that don't change with rotation of axis or which stay unaffected under transformation from one set of axes to another. Subsequently, the combination of stresses at a point that don't change with the introduction of coordinate axis is called a stress invariant. The next chapter is plane stresses. Numerous metal shaping procedures, including biaxial condition of stress on the off chance that one of the three normal and shear stresses acting on a body is zero. The set of stress is called plane stresses. Condition all stresses act parallel to x and y axis. Plane pressure condition is gone over in numerous engineering and forming applications regularly. A slip can be simple if the shear stress following up on the slip planes is adequately high and acts along favored slip direction. Slip planes may be inclined with respect to the external stress acting on solids. It becomes necessary to transform the stresses acting along the original axis into the inclined planes. Stress change ends up essential in such cases. The next chapter of stress transformation in plane stress. Consider the plane stress condition acting on a plane as shown in this simulation. Let us investigate the set of stresses onto a transform plane which is inclined at an angle theta with respect to x and y axis. Let by rotating of the x and y axis through the angle of theta, a new set of the axes which are x plane and y plane will be formed. The stresses acting on the plane along the new axis are obtained when the plane has been rotated about the z axis. In order to obtain these transform stresses, we take equilibrium of forces on the inclined plane both perpendicular to and parallel to the inclined plane. Thus, the expression of the transform stress using the direction cosines can be described as a specific formula. The Morse circle for plane stress. The transformation equation of plane stress which are given in the mentioned equation can be represented in a graphical form by Morse circle. The transformation equations are sufficient to get the normal and shear stresses on any plane at a point. With Morse circle, one can easily visualize their variation with respect to plane orientation theta. Stress relation. In the previous section, the set of stress at a point was characterized by six components of stress, and the internal stresses and the applied forces are accompanied with the three equilibrium equations. These equations are applicable to all types of materials as the relationship are independent of the deformations or strains and the material behavior. Also, the state of strain at a point was defined in terms of six components of a strain. The strains and displacements are related uniquely by the derivation of the six strain displacement relations and compatibility equations. These equations are also applicable to all materials as they are independent of the stresses and the material behavior and hence, irrespective of the independence nature of the equilibrium equations and strain displacement relations. Usually, it is essential to study the general behavior of material under the applied loads, including these relations. Strains will be developed in a body due to the application of a load, stresses, and deformations, and hence it is become necessary to study the behavior of different types of material. In a general three-dimensional system, there will be 15 unknowns, namely 3 displacement, 6 strains, and 6 stresses. But we have only 9 equations, such as 3 equilibrium equations and 6 strain displacement equations, to achieve these 15 unknowns. It is important to note that the compatibility conditions are not useful for the determination of either the displacement or strains. Hence, the additional 6 equations relating 6 stresses and six strains will be developed. These equations are known as constitutive equations because they describe the macroscopic behavior of a material based on its internal constitutions. The linear elasticity generalized Hooke's law. Hooke's law provides the unique relationship between the stress and strain, which is independent of time and loading history. The law can be used to predict the deformations used in a given material by a combination of stresses. The simulation deals the analysis of strain and stress-strain relationship through particular sections, concept of normal and shear stress, principal stress, plane stress, Morse-scale stress invariance, and stress equilibrium relations are discussed in analysis of stress sections, while strain displacement relationship for normal and shear strain compatibility of strains are discussed in analysis of strain section through geometrical representations, linear elasticity, generalized Hooke's law, and stress-strain relation for triclinic, monoclinic, orthotropic, transversely isotropic, fiber-reinforced, and isotropic materials, with some important relations for elasticity are discussed mathematically. And here I can see the SolidWorks simulation that I have applied force as external loads about 100 Newton and made a fixed geometry as a fixture, and I used and applied the material, a specific material for this geometry, and the mesh that I have used is a quadratic because of the selecting finite element method approach for computing the stress strain and displacement for this simulation. Thank you so much for watching my tutorial video until the end. Today is the last day of January 2026, and the time that I am recording this simulation for you is 7:37 o'clock in the morning.